So the final piece of this unit is to kind of take everything we've done with systems and inequalities and apply them to what are called linear programming questions or optimization questions. Before we kind of get into the how, just really want to kind of clarify what linear programming is, right? Linear programming is the mathematical process. It's a process, right? So it's got steps, it's got rules, it's got pieces that have to kind of fall into place. But it's a mathematical process used to find the best solution for a given scenario. So, whoops, my bad. So I told you there were steps, right? We like to have steps, we like to have rules we follow, we like to know what comes first and then what comes next. So take a second, I'm gonna lay out the steps that we're gonna use. First step, we're always gonna define our variables. We are going to use Desmos to draw our graphs for us, and Desmos can only do X and Y. And so when we're making a problem, even if we're talking about cars and buses, we still have to live in the world of X and Y in order to be able to transfer our math to the computer. So that's just something to be mindful of, is when you're picking variables, there are letters that make sense, but there's also letters that work, and we need to use letters that work right now. So call X something, call Y something. But make sure you know what they are and what they're representing. Next key piece. We're going to identify what are called constraints. There are rules to these linear programming questions. Rules that we have to follow, rules in terms of what we can do with the math. Basically, we're going to write some inequalities. In other words, something like they can only produce at most 400 t-shirts and 200 sweatshirts, right? There are rules around it, and those are constraints. We're going to do them in terms of inequalities. So we're going to take the math and put it into inequalities. Okay? Then we are going to write an objective function. The objective function, also known as maybe the profit function, is basically what is being maximized or minimized. We sometimes will have profit that we're trying to maximize or cost that we're trying to minimize. Then we're going to take all of those constraints and we're going to graph what's called the feasible region. Okay? We are going to identify the vertices of that. We're going to substitute our vertices into the function, right? Ordered pairs, x's and y's. Because we want to see which one of those gives us either the highest profit, lowest cost, things like that. And then based on what we get, we're going to identify our solution. Just really quickly, basically you're going to end up with a graph that looks like this. You might have a constraint that kind of does something like this. You might have another constraint kind of, whoops, excuse me. I'm trying to draw this beautiful house here. Another constraint that dives down, and then maybe a third constraint coming straight up. This area inside the house, so to speak, is your feasible region, formed by your constraints and then this would be one of those vertices. Same here, here, here. Those would be kind of those key points. So just kind of trying to tie some of that vocab to where it's coming from. A lot of steps. Check out maybe an example and see kind of what you can come up with.